Okay, let us dive into making this a little bit difficult and explaining how this was actually done in a realistic experimental. So, this is an experiment we did back in Zurich on the device that looks like this. You have a 3 quantum dots, and we were measuring this device as a 2 double quantum dots. Dot 1 and 2 for the first double quantum dot, and dot 2 and 3 for the second. And then it's the voltages on these plunger gates. So we start from the same charge stability diagram that I showed you in a previous section. And indeed, we exactly did the workflow as we explained previously. We measure a small patch, then we have a deep convolutional neural network. That's a type of neural network that is specifically useful for analyzing images. And then we created labels that are very much in spirit of what we explained before. Is there a horizontal transition, vertical, or both? And then we tune in the really 2 steps. First, we go to a 0, 0 state, and then we find the charge state that we want. I am going to explain it in more detail in a second. Let us first concentrate on how to train this neural network. So just to give you an idea of a data volume that you might need for this kind of exercise, we measured 128 of full charge stability data. And then we introduced some augmentations on these data to generalize it even more. To, for example, create a little bit of a skew so your charge lines would go in a slightly different angles, introduce a slight rotation, things like that. After that, we completely randomly drew many patches. Now, in a sort of theory starter part of this lecture, I just told you that per patch you will do one label. Non-transition, horizontal, vertical, or both. We do actually 3 labels here. It's a slightly more complicated architecture, but the philosophy works just as well as with the simple one we explained. Basically, it's to really have a redundancy. So we label corner 1, corner 2, and corner 3, that we say with respect to, for this corner, I am seeing this transition. For this corner, I am seeing both, and for this corner, I am seeing this transition. Ideally, they will be consistent with each other. But if they are not, you will get some redundancy in your label to weed out any immediate mistakes, which can easily happen based on where your square is drawn in your data. You can think about how this would come up. So we have these 3 labeled squares, and like we said before, we put into neural network, we run it through the neural network, and we output all of these labels. For individual patch like this, we reached an accuracy almost 99% on a test data for the trainings. Now, as I said, we are going to actually tune up this device in 2 steps. First, we find 0, 0. That's what we did already in a previous section. And once we found 0, 0, we can think about how to shift in a specific charge state. Here is an example. How would you go to 3, 2, and so on. So here you notice even visually that there is a difference between window size in the first part of the algorithm and in the second part of the algorithm. And this is 1000% true. We actually trained 2 individual models for each. Because when you are looking for 0, 0, it's really important you don't end up in a place of your charge stability diagram where maybe you have some line, but your classification has missed it. So we took a bigger window because if we are a little bit too to the south, it's suboptimal, but it's not super bad. And we have 100% security that we arrive to a 0, 0 state. Once we are there, it's super important not to miss any transitions. So we draw the windows in a smaller way. So in practice, these are the measurement runs on an actual device. first thing I want you to notice is that the data from these patches, if you compare them to this beautiful charge stability diagram we showed at the beginning, they are really noisy. And sometimes I have to say that I would be hard pressed for myself to actually guess, is there a transition here or not? But somehow, even for a really noisy data where I cannot tell by naked eye, the neural network is really good at recognizing it. And these are sort of two examples, one very short, one a little bit longer, how to go from 0, 0 to 2, 1 on these double quantum dots. In classification machine learning, to characterize the full results, we use something called confusion matrix. It looks, maybe it's a lot of numbers, it looks a little bit confusing, but it's actually very simple. So on one axis, we want to put what the correct label would be. On the other axis, we put the actual correct labels and we count. So for example, this means that the ideal situation is that I want to have a numbers only on the diagonal. Here, for example, 28 times the label was 1, 1, and we also predicted 1, 1. However, 9 times the label was 1, 2, but we predicted 1, 1. And this is how you can read this matrix. So basically, every deviation of diagonal gives you an important source of error. And what you will see that we have quite some numbers that are below the diagonal, because in practice what happened is that even though the neural network is sometimes better than a naked eye at distinguishing these transitions, it does not do that every time. So we missed quite a few transitions when we were doing statistics on this device. In 160 tuning runs, we found 0, 0 with 90% success, and for an arbitrary charge state, we had about 60% success. The good news is, though, that this success was independent of which of the double quantum dot you run the device on. So it really ended up being not dot specific and quite general. So this was back in 2020, and it was one of the first example of doing this kind of thing. And looking at the numbers, you see that it's starting to work. It's really great that you get this automated tuning without a human assistant. But at the same time, to have the devices really fully operational, we need quite some push in a success accuracy. So this I'm going to explain in a next section.